Before we dig deep into specific wide area network technologies here in Module 4, we want to go ahead and take an overview of wide area networking in general, and then we'll dig into all the great details of designing wide area network solutions and remote access and VPN solutions inside this very, very important edge distribution module. So let's go ahead and jump right in and discuss wide area networking technologies that we would have at the enterprise edge of our modular Cisco network infrastructure. We know that WANs are unique animals. WANs, wide area networks, are indeed going to span large geographical distances in order to provide connectivity to key ingredients in our network infrastructure. We know that unlike the local area network environment, we tend not to own everything that is associated with the wide area network. Instead, we are going to be renting or leasing equipment and connectivity from service providers, or they're often called carriers. And these days, these carriers are well trained to make sure they carry for us not just the data traffic that would be traditional, but also voice and video services as well. So when you talk to your providers and carriers these days, they're ready, willing, and able to typically, by the way, they're typically willing and able to carry data, voice, and video traffic for you across these large, potentially geographical distances. Notice that another interesting thing about WANs, unlike LANs, is that we typically have some initial fixed costs that we need to spend, and then we are going to set up a recurring type fee structure typically. So with wide area networking, not only do we not own everything, not only do we have to come up with this payment to a provider, but it's probably going to be on a recurring basis. This is definitely one of the reasons why we tend not to engage, okay? We tend not to engage in the approach of over-provisioning. Remember when I was talking about quality of service? Yeah, something that we'll definitely be revisiting in depth today. When we were talking about quality of service, we were talking about how one overall approach would be to basically ignore it, basically just deal with quality of service by dramatically over-provisioning the bandwidth in your network infrastructure. Well, certainly one of the reasons that we shy against this approach, over-provisioning the bandwidth, is in our wide area networks, the high costs that doing so would lead to. So we definitely want to watch out for the high costs associated with the recurring fees that we would run into with over-provisioning the bandwidth. Design requirements, by the way, when we're looking at wide area networking technologies, we'll obviously get into much greater detail in this in later lessons, but I just wanted you to overall here, as we talk about these specific wide area network technologies, I just wanted you overall to be thinking in terms of what applications are you going to have to support? How available do those applications need to be in the various areas? How reliable do those applications need to be in the various areas? And how much we can spend, what are going to be the costs associated with a particular wide area networking technology? And finally, what kind of usage are you going to have? I mean, really, what kind of bandwidth are you going to need for these various applications and for these various usage levels? The enterprise edge. We know it is in a large enterprise, a large block or several blocks of equipment. We typically do indeed take the large enterprise edge block, and this is certainly a review from our day one materials, but we typically do take this huge enterprise edge module and we typically do break it up into submodules. The reason we need to break it up into submodules, of course, is because there is such specialized functionality for the overall functions of the enterprise edge. We typically need robust internet access with some level of availability, some level of redundancy, etc. We typically need a demilitarized zone, a DMZ area. We typically need a WAN component for our branch office remote access connectivity. We typically need an e-commerce if e-commerce is a big part of our organization. And we'll be talking today about remote access VPNs. This is a very, very exciting option to provide secure connectivity for the large numbers of employees we tend to have these days that are roaming the world. Or how about the large number of employees that we tend to employ these days that work out of their small office, home office environment? I'm certainly a poster child for that particular employee. Something that you need to be well versed in for the CCDA certification is the common categorizations that our varied wide area networking technologies will be lumped into. There is the concept of circuit switched technologies. And great examples of circuit switched technologies would be those involving the public switched telephone network. A great example of this would be ISDN technologies. ISDN technologies are a great example of a circuit switched technology. What happens with circuit switched WAN connections is they're established when we need them, okay? So they're established when we need them, and then they're going to be torn down or terminated when we do not need them. Another great example of this is the old-fashioned now. We look upon it with a smile. The old-fashioned dial-up modem analog access over the public switch telephone network. Another perfect example of circuit switch technologies. I imagine there's still plenty of people dialing up to the internet to this day, but obviously their numbers are fewer and fewer and fewer. Boy, it's so funny to think about that, isn't it? That not too long ago, that was our primary way in which to access internet resources. We'd plug in with our RJ11 jack, would plug our PC into the wall jack. We would then dial up, we'd hear the screeching and hissing, and we would access our internet resources and maybe even create a virtual private network connection using about, on average, what would we get? About 40 kilobits per second, 42 kilobits per second. Now, the opposite of the circuit switched option would be an leased line, a 100% dedicated connection. Absolutely 100% dedicated connection, a leased line connection, dedicated, permanently up. It is your company's line. We'll talk about something in this course called time division multiplexing, and an example of a leased line would be one of these time division multiplexed leased lines. Expensive? Yeah, very, very expensive typically, because you own the thing, you have sole use of the connectivity, and you're paying for that privilege. Another popular category of wide area networking technologies is packet switched. In a packet switched infrastructure, we have shared bandwidth that utilizes virtual circuits. So interesting, there's all this bandwidth that the provider has, and you create what appears to be a leased line through this bandwidth, this cloud of bandwidth. So you create a virtual circuit. It can even be a permanent virtual circuit, and it really looks and feels like you have this leased line, you have this dedicated bandwidth. even though technically you don't. Frame relay is a great example of this type of technology. We'll talk about frame relay intensively in this course since it is definitely a huge part today still of Cisco certification. Even though frame relay is getting less and less popular with every passing year, it is still a huge, huge part of Cisco certification. Another category of wide area networking technologies is cell switched. Now, one of the things you often see is you often see this included with packet switched. It's so absolutely similar. It's just that this one premier technology called ATM, it operates almost just like a packet switch technology. There is one major difference, though. It operates utilizing fixed length, fixed size cells. So instead of using what we would call packets, like in frame relay, ATM uses these small little fixed length cells, and that's why it's often referred to as cell switched technology. I went ahead and decided to break out cell switched here in our presentation and separate it, distinguish it from packet switched. Okay, so these small fixed length cells that are utilized. And again, it's a shared bandwidth environment as far as the provider goes. They've got a bunch of equipment that can do ATM, and they're going to guarantee you some level of bandwidth service through their ATM equipment in the cloud. Broadband is another growing category for wide area networking. In the broadband category, we'll take a look at DSL, we'll talk about cable, we'll talk about wireless options that are all kind of generically lumped under this category of broadband. So notice there are lots of options today when it comes to wide area networking, and it's really no surprise that there are this many categories and this many technologies that we're going to talk about, because what have we been saying again and again in this course? Modern networks feature the need to access about 80% of stuff that's no longer local. Remember, we've turned that 80-20 rule like upside down on its head. It used to be that most of the stuff we were accessing was local. A small amount of it had to be accessed over things like WAN connections. Now we've turned that whole model on its head. Turned it right upside down. And we have created an environment where the vast majority of all of our connectivity has to go out to remote resources. Wide area networking topologies are also categorized. We've talked about the full mesh, haven't we? We've talked about the full mesh, and we presented the formula for you that would demonstrate just how out of hand quickly full mesh topologies can get. That formula was n times n minus 1 divided by 2, wasn't it? And that was the formula for just how many connections we're going to need in a full mesh infrastructure. We showed you a site that had 4 nodes in it. There were 4 nodes that we wanted to connect in our particular topology, and we saw that that was going to require 6 different connections. 6 different connections as a result of those 4 nodes if we wanted to operate in a full mesh. Full mesh is absolutely wonderful. I mean, full mesh is great, right? For availability and reliability, because if there is any kind of failure, we can have this fallover occur. Failover, we tend to call it, this failover to the other links that are in existence and the other devices that are in existence. So full mesh, yeah, it's wonderful as far as availability and reliability go, but gosh, what overhead on us for setting up all those connections. And then, of course, we also have to worry about the cost associated with all of those connections. So of these three categories, full mesh certainly is something that is appealing to us from the standpoint of availability and reliability, but we shy away from it when it comes to cost, and we shy away from it when it comes to the overhead that is going to be associated with building and maintaining all of those many connections. Something that is the most popular option when it comes to wide area networking topologies is what's called hub and spoke. So maybe here is our corporate headquarters, and we have a hub router, and this hub router makes connectivity out to branch office routers. So, this is an office in Reno. This is an office in Tampa. This is an office in Boston. This is an office in London. And these various branch offices connect in this hub and spoke like fashion. Notice, while this is popular, this doesn't do all that great wonder for us for our redundancy and availability. As a matter of fact, if you had a key location, you're probably going to want to drop in a secondary link, right, for that key location. Still an overall hub and spoke design, but some key locations may feature backup links, and the backup links are there to make sure this key remote office has some redundancy in its design. So hub and spoke WAN topologies are the most popular. Notice we are not having to go crazy with the number of circuits. We've got 1, 2, 3, 4, 5 nodes in this illustration, and we've got 1, 2, 3, 4 primary nodes and 1 backup node. So we compare this to the full mesh, and it is far, far less complex, far less expensive to set up. Another environment, another topology that we can run into when it comes to wide area networking topologies is the partial mesh. And what you're dealing with in a partial mesh is you've got some kind of fully meshed areas, and then some like kind of hub and spoke areas. You don't have a full mesh, you have a partial mesh. I guess it's that easy to describe. Okay, so it's somewhere in between the full mesh and the hub and spoke. There may be fully meshed areas, and then it leads off to areas that aren't fully meshed. So somewhere in the middle of these two, hub and spoke and full mesh, we have the partial mesh option. This is great when you've got to have that high level of availability and redundancy for certain nodes, but certain nodes just don't deserve that kind of treatment. Now, something else that I wanted to really go into detail with you here as we kind of take an overview of wide area networking technologies is I wanted to go into some great detail with you on non-broadcast multi-access technologies, because they do present challenges, these non-broadcast multi-access technologies that we don't have with our native broadcast technologies. And we're going to be discussing a lot of these technologies in this course. So I wanted to go ahead and really focus on what happens when there is no native broadcast support for a bunch of different systems that can all be communicating on the same network. What kind of issues do we run into when you can't broadcast? When natively you cannot send a packet that is addressed, that is destined for all of the devices on the multi-access segment. Examples of these technologies, ones we'll be focusing on here, are like frame relay, right? ATM, ISDN. These technologies are classically non-broadcast multi-access. X.25 we will not focus on in this course. X.25 is kind of like the predecessor to frame relay. You will still find it implemented out there, but it is getting more and more rare to find. Again, it can be looked at as the predecessor to frame relay technologies. So all of these technologies, amazingly enough, don't have any native ability to support broadcasting. So what do? I mean, certainly if they're running like routing protocols these days use a multicast approach. And by the way, in this course, whenever we say the word broadcast, I want you to also be thinking about multicast. Okay, so when I say broadcast, yeah, I want you to also think multicast. The two technologies go hand in hand. Okay, so broadcast and multicast, very, for our discussions here, they are identical. We know they aren't identical by any means, but for our discussions here, they are identical. So no native broadcast or multicast support when it comes to these technologies. So in the case of a routing protocol, oh my goodness, a routing protocol is going to use multicast in its operation. We got to get those routing protocol updates to all of these nodes that are participating in the NBMA network. What in the world are we going to do? Well, the approach that can be taken is the devices can go ahead and they can take the broadcast or the multicast traffic and they can send it as replicated unicasts. Ah, interesting. So they'll take this broadcast or multicast frame and they'll go, okay, I need to send this frame to node A as a unicast, to node B, to node C, to node D, to node E. It replicates them as unicast to all those devices. Uh-oh. Uh-oh. That means the device has to be able to come up with a way to solve layer 3 to layer 2 resolution. It now has to address these particular packets for the specific machines out there that need to receive these packets. I mean, think about the ISDN cloud, right? The device cannot call every possible phone number that exists in the ISDN cloud. So there's got to be methodologies for resolving the layer 3 to layer 2 name resolution here. The layer 3 address, by the way, is typically the IP address, right? And then the layer 2 address, that's going to vary per the technology used. In the case of frame relay, which we'll look at in depth today, frame relay is going to use the data link connection identifier as the layer 2 address. So funny how my pen sometimes freaks out on these slides and draws that huge diagonal line. If you haven't already figured it out, anytime that is to happen, just ignore it, right? So anyways, the data link connection identifier, that's the layer 2 address that we would have in frame relay, and we need to figure out a way to resolve that to the layer 3 IP address that we are going to utilize in conjunction with frame relay, of course. Layer 3 name resolution is needed, like we talked about, to bind these layer 2 addresses. And this is a concept that we're already very familiar with from our broadcast-based networks, aren't we? Sure. In our broadcast-based networks, we've been talking about MAC addresses. And those MAC addresses need to be resolved to IPv4 addresses. And this is done thanks to the address resolution protocol. In a broadcast-based network, the device broadcasts a request. It says, hey, I want to communicate with 1, 2, 3, 4. And this is typically learned from DNS. The IP address is learned from DNS. And then the device is ARPing out there on the network to say, what's the MAC address that goes with that device? Hopefully we get a unicast reply, and that unicast reply is with the MAC address that coordinates with that particular IP address. Notice in a broadcast-based network, it is an initial broadcast, and then there is this unicast response to that initial broadcast. Now, as we'll see, in non-broadcast multi-access environments, We still need to bind this layer 2 address to the layer 3 address. Like I said, in frame relay, we have something called the local layer 2 data link connection identifier that has to be binded with the IPv4 address. Maybe it's a remote ISDN phone number that we have to bind to a remote IPX address. So there's going to be this layer 3 to layer 2 resolution that has to occur in the NBMA environment as well. There is a technology to do this in an automated fashion, and this is called inverse ARP. And it is used to resolve the remote layer 3 to a local use only layer 2 address. We'll see inverse ARP can be utilized in frame relay environments. But the issue with inverse ARP as the solution for name resolution in an NBMA environment is that, notice, it is going to be limited to directly connected devices. Only directly connected devices can engage in this, so this definitely immediately brings up issues with our partial mesh NBMA networks. Now, one thing we have to understand is that there are going to be different types of non-broadcast multi-access interfaces. One of the types of NBMA WAN interfaces that we can run is called the multi-point type. As its name implies, it can be the termination point for multiple layer 2 circuits. And sure enough, we're going to require some layer 3 to layer 2 resolution methodology. If we configure frame relay on the main physical interface of a device, yep, we are multi-point by default. And if we create a sub-interface on a frame relay physical interface, it is going to be, it doesn't default to anything, but we do have the option of creating it as multi-point. You go in and you create it multi-point by saying, okay, interface serial 0/0.1. That creates the sub-interface, and then you use the multi-point keyword in order to make the interface multi-point. So if we create a frame relay multi-point sub-interface, yep, same deal. We have to go ahead and provide for the layer 3 to layer 2 name resolution for that multi-point sub-interface. There are, as we've already discussed, two options in frame relay for doing this. There's inverse ARP, and the more popular option, because it always works if we set it up correctly, we can statically map. So your frame relay design will feature static maps that are used to provide the layer 3 to layer 2 name resolution that you need. But I've got great news for you. Layer 2 to layer 3 name resolution doesn't always have to be an issue in your non-broadcast multi-access interfaces, because you can create point-to-point wide area network interfaces. If you're point-to-point, by very definition, you can only terminate one layer 2 circuit. So if there's only one device out there that you communicate with, by definition over the point-to-point, you don't need any of this stinking layer 3 to layer 2 name resolution. With only one circuit, there's only one possible layer 2 address out there for you to communicate with. So these issues of name resolution disappear when we are running, for example, a frame relay point-to-point sub-interface type. Or for that matter, if we have organized an ATM point-to-point sub-interface type. Awesome. So point-to-point non-broadcast multi-access interfaces give us the joy of having a name resolution free environment. Well, let's go ahead and do some exam review as we wrap up this overview of wide area networking technologies. We're asked to provide 2 examples of NBMA technologies. Oh gosh, 2 examples of NBMA technologies. Yeah, 2 that jump to mind, frame relay and ISDN. Yeah, there's the predecessor to frame relay, X.25. In fact, we could even think of a 4th easily. There's ATM, that cell switched technology. That cell switched technology is also non-broadcast multi-access. What are 3 different WAN topologies that we could utilize? Well, that's easy. The popular hub and spoke, or the full mesh, or the variation of both of those types, the partial mesh. And finally, can you name 4 different WAN categories? What are 4 different major category types for your wide area networks? The answer, we've got our packet switched, our leased line, our cell switched, and our broadband technologies. 4 different wide area network categories. Packet switched, leased line, cell switched, and the generic broadband, where we tend to put everything else. DSL, cable, wireless technologies, all lumped into that area of broadband. By the way, the term broadband, pretty neat. Broadband refers to your ability to take a connection, like the old-fashioned coaxial that comes into your house for you to get cable TV, and to figure out how to use different aspects of that bandwidth. So, traditionally it might be the TV that was going through the coaxial, but then what they figured out is how to use technology called multiplexing inside that cable to figure out how to get like internet data across. So I love that term broadband, figuring out how to go in and get additional bandwidth out of a particular meter. Very, very cool technology. Well, all right, folks, great job in this first Module 4 lesson where we have taken an overview of wide area networking technologies. As you might guess, what we're going to do next in this course is we'll start focusing on particular types of WAN technologies. So we talked about frame relay, for example. We'll get intense in frame relay. We talked about ISDN. We'll get intense when it comes to ISDN. We'll explore the various workings and design considerations for each of these wide area networking technologies.